big fan of the San Lorenzo River. So, as you probably recall, last winter, it seemed like it never stopped raining for about 2.5 months. This was good for our state's water supply, but it was also pretty inconvenient and even dangerous at times. It does give us an opportunity to learn more about how this type of small, steep watershed, which is a terrain that's very sensitive to changes in climate, responds when we go from very dry to very wet conditions. Under 21st century climate change, the magnitude and the frequency of storms is widely expected to increase in many regions. And in the western US, climate models predict that we will see major droughts in the future, punctuated by some years where we have more intense storm activity than we've commonly had in the past. So this type of swing from very dry to very wet conditions is essentially what's happened in California over the past 5 years. Between 2012 and 2015, the western US had one of the worst droughts in known paleoclimate history. We had the worst drought in the past 1,000 years. Then, in this area, we had one sort of average water year, which was the water year of 2015-16. And then we went to very, very wet conditions in 2017. So we can study river response to these extreme swings from very dry to very wet of the past 5 years with an eye toward conditions that will probably shape rivers and riparian habitat in the future. Understanding how sediment from coastal watersheds responds to extreme dry versus extreme wet years has important implications for how we expect flood and landslide risks to progress in the future. It also has implications for coastal sediment management questions like maintaining and dredging harbors, beach nourishment in places that have to nourish beaches, and also for habitat and ecosystems. In watersheds that store water behind dams, there are also implications for how our water storage capacity will change in the future and how fast reservoirs may fill up. So, what happened last winter? Over much of the western US, 2017 was one of the wettest winters in the modern era of weather data collection. And this map I'm showing here on the right is a map from the Western Regional Climate Center showing the western US precipitation from October to March 2017. So the water year begins October 1st of 2017, and this is precipitation through, from October through March last year. The areas in this pale green color are places where it was in the above normal category, so in the top 1/3 of weather data history for that region. This bright green color is places that were much above normal, so in their top 10% for that region. And in the dark green are places where it was the record wettest October to March. And our San Lorenzo River Valley is actually one of these dark green places where, according to the PRISM algorithm that the Western Regional Climate Center uses, it was the wettest October to March, wettest winter on record. Most of our rain in 2017 came from atmospheric river storms, which are narrow bands of spatially concentrated low-altitude water vapor flux that tap into tropical heat sources. This is an example of what that looks like on a map of vertically integrated water vapor in the atmosphere. So this is the west coast of the US, and this is an image from a storm in 2006. And there's all this warm and high flux of water going from tropical latitudes, making a beeline up toward the west coast in this very narrow band. These air masses are very warm, so they can hold a lot of moisture. And a lot of atmospheric rivers cause flooding on the west coast because when they get to our coastal mountains along the west coast, they move up, and then they start dumping rain. A lot of atmospheric rivers cause flooding for that reason. From Northern California up through the Pacific Northwest, most flooding and most landslide activity occurs from this type of storm. In 2017, the amount of water vapor we had coming from atmospheric rivers was abnormal, not just by a little bit, but by a huge amount. It was really an unprecedented amount. In statistical terms, it was 3 standard deviations above normal. So we can keep an eye on this type of system, thinking this is the type of system we're going to have to deal with in larger numbers and probably greater intensity during some years in the future. So in the San Lorenzo Valley, I'd like to show you how sediment export from this watershed has been varying as we went from very dry to average to very wet conditions. It's varied enormously, even though we never had one singular catastrophic event. When this weather pattern happened last year, we never had a huge storm that caused a 100-year flood or anything like that. Instead, what we had was multiple closely spaced storms that kept causing floods that normally have 2 to 30-year recurrence intervals for floods those sizes. So we didn't have any one enormous flood, we just had lots and lots of moderate-sized floods. This watershed has a really interesting ecological history and human land use history, as we've heard some about. Today it's moderately urbanized, and it's still affected by a legacy of intensive logging that took place mostly prior to 1905. The coho and steelhead in this area are endangered and threatened respectively, as we'll hear more about next. The USGS science that I'm talking about today builds on earlier studies by Gary Griggs at UCSC and by Kit Conaway and Andy Ritchie and myself at the USGS. Our studies in this watershed, in addition to 2 stream gauges that the USGS maintains, we also collect water samples from downtown Santa Cruz, and we have a long-term project monitoring the topography along the beach and just offshore and all throughout Monterey Bay, actually. So these are plots of discharge and rainfall for water years 2016 and 2017. The top plot is discharge of the San Lorenzo River measured downtown. This is discharge in cubic meters per second, and these horizontal lines are showing you the magnitudes of the 2-year flood, 5-year, and 10-year flood. When I say that the 2-year, 5, or 10-year flood, for instance, the 2-year flood just means the magnitude of flow we would expect the river to get up to about every other year. The bottom plot shows rainfall in the San Lorenzo Valley that I've averaged over 5 rain gauges. The black lines are daily rainfall rates, and then the gray shaded area is cumulative rainfall over the water year. So in water year 2016, we had about an average water year, and there was one high flow event that got almost up to the 5-year flood. Whereas in 2017, our very wet year, we had about 165% of average rainfall. You can see it's much, much higher here. And we had 9 flood events, 9 times that the flow got over the 2-year flood magnitude. 4 of those events got up to or above the 5-year flood, and 1 was above the 10-year flood magnitude. We sampled water over water years 16 and 17 using a depth-integrated sampler that we have mounted on a station along the pedestrian bridge downtown between Water and SoCal. It's right next to the Trader Joe's. We collect water samples over a whole range of discharge conditions, and we try especially to hit the high flows. Then we analyze these for sediment concentration and the sand proportion, so trying to see how much of the material in the water is coarser grain sizes than 63 microns. Our data collection got pretty exciting at times last year. We were out on the bridge in all weather, day and night, and this is not automated sampling. This is me and my friend Andy going out to the bridge and physically dunking the sampler in the river. And I want to thank the city rangers and the Santa Cruz Police Department for keeping an eye on our safety at times. So this is what the 10-year flood peak looked like on February 7th last year, if you didn't get to see it. This is the same flood peak viewed from the other side of the river. The courthouse is just right over here, and this is where the river bank normally would be. This is the atmospheric river of water samples on the floor of my office. We collected, I think, 112 samples during last year's storm. So we used these samples to determine a relationship between sediment concentration and river discharge. Then we take the rating curves that we calculate from those and use them to calculate what the total sediment load is for any given storm or for the whole water year as a whole, once we've determined that statistical relationship. And these are just the samples that we collected. Okay, so here I've plotted up annual sediment load in the San Lorenzo River for the past 10 years, including a projection for where I think 2018 will probably end up. So this is this is 2009 through 2018, and this is annual sediment load in metric tons. And what I've done here, I've color-coded this. It might be a little hard to see, but these orange points are the dry years down here, and these are the average to near average years in light blue. And 2017 plots up there at about 427,000 metric tons of sediment coming out for the year. This is about 10 to 12 times the sediment export we get from this watershed in an average year. And it's 500 to 600 times more sediment than we see coming out of this river in dry years. So it really varies over an enormous range. For 5 of these 10 years, we actually have direct measurements, and then for 2011 to 2015, I've hindcast what it probably would have been given the 15-minute discharge record, even though we don't have direct measurements. We just use those statistical curves to estimate for those 5 years. For 2018, I ran the calculations through Tuesday night, and we've got about 800 tons that come out of the river this year. which is much less than 1% of the amount that had come out of the river by this time last year. So we're seeing this enormous variability as we go from very dry to average to very wet conditions. The watershed apparently had some interesting changes during 2017 also, and you can see this looking at what's happened on high flow events of the past few years. So in these plots, I've pulled out 19 high flow events from the 4 years where we have measurements right during the high flow peaks. I'm using data from water year 2009, 2010, 16, and 17, and just looking at 19 high flow events, 9 of which happened during water year 17. So in the top plot is river discharge, showing you how high the flow peaks got in each case with the black dots. And then the circles show you how closely our sampling is representing what happens during the flow peak. In the middle plot, what I've done is taken the maximum sediment concentration during each high flow and then normalized it by a measure of how high the flow is getting up to. So it's basically the concentration per unit discharge here. And the bottom plot is how much sand was in each of those high flow events. So I'm looking at the grain size of what's in the water. And what you see here, if you look at changes after about early January 2017, after our second or third flood of the 9 floods we had last year, both this blue line and the tan line start to go up, and they stay at higher values for the rest of 2017. This means that for a given discharge, we were seeing a lot more sediment in the water, and it's composed of coarser grain sizes after those first couple floods. This suggests that something was changing in how the watershed was actually functioning as we went through that high flow season. I think landslides are the most likely explanation for those changes that occurred after early January. Many slopes started to fail up in the watershed last year, which is not surprising given how steep a lot of this basin is, and that can generate a lot of new debris that moves down into the river. Not only landslides, but also when a tree falls over from its root base, it often dislodges a lot of material that moves down slope into the stream network. We don't have direct measurements of landslide area or volume, but we do have some information about landslide timing that supports the interpretation that that was what was causing these changes in the river's character and what it was exporting. Again, here's the plots of river flow and rainfall for last year, and this is data from the County Planning and Public Works Department showing the number of slope failures reported to have damaged roads and property last year. So you can see this is just in the San Lorenzo Valley. There were many, many more than this, but I pulled out the ones just in this watershed. There was 136 of those damaging landslides in 2017, as opposed to 4 the year before. And the timing of when the reports started to come in starts in early January and just ramps up and up and up through January and February. The timing of when people report a damaging landslide isn't necessarily the date that it occurred, but in general, the timing does correspond to when we started to see this shift. And there's also a lot more landslides that happened in the watershed that were not in this database because they didn't damage roads or property. Here's a slide that comes into the river just upstream of the Garden of Eden. So, and then this is a plot of rain intensity and duration using data from Ben Lomond last year, just to show that multiple times during last winter, we had rain intensity and duration that was well above this curve, which is where threshold, the assumed threshold for when widespread landsliding starts to happen in the Bay Area terrain that we have. So when you have it rain that is longer lasting and more intense than what you get on this curve, you expect lots of landslides, and we certainly had rain that met those conditions. So although we don't know the total landslide area or volume or number last year, we know landslides were active in large numbers and that their timing roughly corresponds to these changes we see in the river sediment. There's still a lot of sand parked in some of the creeks up in this watershed. This is Eagle Creek in Henry Cowell, which is one of my favorite tributaries of the San Lorenzo, Chris. This is a very unusual thing to have a steep sand-bedded river like this with that much sand just sitting there. I would have expected this to flush out more this year than it has. We just haven't had a lot of runoff this year. But there's a lot of sand that could still move downstream, and I would expect this signal of elevated concentrations and grain size in the river to persist for probably 5 to 6 years, and it's likely having effects on fish habitat too. Just to wrap up, let's look quickly at the effects right along the coast. I'm showing plots on the left here. These are maps of the northern part of Monterey Bay. This is the Santa Cruz Wharf. Here's the San Lorenzo River mouth. This is the harbor. And these are change in elevation over that area in the past 3 winters. So this is winter 2014-15, which was a very dry year. We don't see a whole lot of change right at the river mouth. There's just this normal seasonal onshore-offshore sand movement. In winter 2015-16, which was an average water year, we did see some new sediment depositing. But in 2017, there was a huge new deposit that formed off the river mouth. It was about 210,000 cubic meters of sediment, which, when you convert it to mass, is about 3/4 of the river's sediment export. And it's still sitting there now. There's this huge pile of new sand sitting right at the river mouth that has not changed in the past years, because we haven't had a lot of wave activity this year. So they surveyed this again last week, and the map isn't ready for prime time yet, but it looks about like this now. This is actually a similar volume of sediment sitting at the river mouth as happened from the 100-year flood of 1982. There was a huge storm in January 1982 that killed a number of people in Ben Lomond from landslides. And that the sediment volume at the river mouth right after that event was about like we're seeing right now, even though the total mass of sediment that came out of the river then was more than we saw last year. So in hindsight, was it predictable to have such wet conditions last year with floods and landslides, given that it was not an El Nino year? We tend to think in California that the wet years are going to be the El Nino years, and in general it's true that rain and flooding and landslides correlate with the El Nino part of the cycle, of the ENSO cycle. But last year was not an El Nino year, and we had this huge water year with lots of hazardous events. And then it's also worth mentioning that that devastating January 1982 storm also happened during a non-El Nino year. So it was actually what we call ENSO neutral conditions. It was neither El Nino nor La Nina. Some meteorologists actually think it's easier to get atmospheric river storms up to the west coast of the US during El Nino neutral years, just because of how the atmospheric flow sets up. So it's worth bearing this in mind for the future, that we might be looking for the most damaging floods and landslides during some of the years that are not El Nino years. And then we have some years when we had a very strong El Nino in 2015-16, and there was a lot of wave activity, but there was really unspectacular river discharge. So it's hard to know what to expect in any given water year, but it's worth keeping in mind that some El Nino neutral years could be some of the riskiest for floods and landslides. Okay, I know I'm out of time, so just to wrap up. We expect in the future our climate will swing from very dry to very wet conditions like it has in the past few years here. And we're seeing 600-fold variation in sediment export from this watershed and probably others like it as we go from these dry to wet extremes. This is going to affect coastal management problems like dredging the harbor and so on, and it's going to also affect fish habitat. We expect the effects of the 2017 wet winter to probably last 5 to 6 years also. Okay, and I'm out of time, so thanks for